Alright, let's continue. Okay, let me open the table of content first. Alright, we are on chapter 22 here, and on section 22.3 simple policy 5.4. Okay, let's continue on this section. Let me open that up. Okay. Alright. Okay. Yeah, this one. A simple policy FIFO or first in, first out. Okay, many early systems avoid the complexity of trying to approach optimal and employed very simple replacement policies. Okay. Alright, for example, some systems use FIFO or first in, first out replacement where pages were simply pages in a queue when they enter the system. Where pages were simply placed in a queue when they enter the system, when a replacement occurs, the page on the tail of the queue, the first in page, is effect. Okay. FIFO has one great strength. It is quite simple to implement, right? Unlike the optimal solution, which is affecting the the furthest for future use or something like that, and we cannot really, and it is hard. It is hard to predict the future. So first in, first out here is quite simple to implement. Let's examine how first in, first out does on our example reference stream, figure 22.2 on page 5. We again begin our trace with three compulsory miss to page 0, 1, and 2. Okay, wait a minute. I think I haven't read this. Okay, let me check that out. Unfortunately, as we saw before in the development of scheduling policies, the future is not generally known. You can't build the optimal policy for a general purpose operating system. Okay, what is the footnote here? If you can, let us know. Okay, yeah. If anyone can predict the future, let us know. Or at least making the optimal policy here. We can become rich together. Or like the scientists who discovered code fusion, whitelist corn and milk. Oh, I'm not sure about the reference. We will take a look at that later on. Okay, let's examine how first in, first out does on our example reference stream, figure 22.2, page 5. We again begin our trace with 3 compulsory miss. If I remember correctly, the cold start miss, something like that, to page 0, 1 and 2, this one. So when we try accessing page 0, we miss, right? So we add 0 to the case, the page 0 to the case, and then the next one, page 1 also miss, right? When we try accessing page 1, also miss. So we add 1 to the case to like this, okay? And then the second one, the page 2, the page 2 also miss because page 2 is not in the case, right? And then we add page 2 in the case, and then we reaccessing, and then we try accessing the page 0 again. It is hit, right? Because page 0 is in the case here. And then we are trying to access page 1 again. It is hit because page 1 is in the case. And then trying to access page 3, we miss because page 3 is not in the case previously. And then we evict or put out the page 0 because it is the first page that we insert into the case, right? The page that first come in, so we evict that, and then we have 1, 2, and 3, the page 1, page 2, and page 3 in the case. And then we try accessing page 0 again. We miss because we already evict the page 0 here, right? To become this one. And then we evict the page 1 in here because it is the first page on the case, right? And then become something like this, the case. Page 3 hit again because page 3 already in the case here. So nothing changed for the case. And then we try accessing page 1, miss. Okay. And then we evict page 2 because it is the first page here. Right, the case becomes something like this. Accessing page 2, miss, and then we evict page 3 because the first page here is page 3. And then the case becomes something like this. Try accessing page 1 again. Hit because the page 1 already in the case, right? Something like that, tracing the first in, first out policy. Oh, hello Luigi, welcome. Yeah, we are continuing chapter 22 here on section 22.3, a simple policy, first in, first out. Basically, what is called trying to understand the policy, the replacement policy of the memory, like how, what is it called, what kind of policy that we need to use when we are running out of memory and then need to replace those memory, like for example this one, what is it called? When we try to access page 3, we hit miss, right? And the case, or let's say the memory already full. So in this case, we move out the page 0 here and then put in the page 3 here, so that it become what is it called, faster, I guess, when we try to access the page 3 again. In this case, like this case, we will be a lot faster because it is already in the case, something like that. Okay, and then hit on both 1 and on both 0 and 1. Next, page 3 is reference cause a miss. The replacement decision is easy with FIFO or first in first out. Pick the page that was the first one in the case that in the figure is kept in first out order with the first in page on the left. Oh, okay. Let's pick the page that was the first one in. Okay. And then the case state in the figure 20.2 here is kept in the first in first out order with the first in page on the left. This one. This is the first in page, and when we need memory from the case, I guess, we will be replacing this left page. Something like that. Okay. It is page 0. Okay, in this case, I guess we are moving out the page 0 from the case, right? Unfortunately, our next access is to page 0, causing another miss and replacement of page 1. Unfortunately, our next access is to page 0, causing another miss and replacement of page 1. Right? We just move out the page 0 from the case, and then the next time we are trying to access the page 0, so we miss, and then we need to move out the first in page here, and that is the page 1 here, and then adding the page 0 again. Okay, causing another miss and replacement of page 1. We then hit on page 3 but miss on 1 and 2, and finally hit on 1, I mean. We then hit on page 3 but miss on page 1 and page 2, and finally hit on page 1. Comparing first in first out to optimal, first in first out does notably worse, 36.4% hit rate or 57.1%, excluding compulsory miss. Okay. Yeah, I mean compulsory miss is when the case is empty here. For example, this one, I guess. So it is increase. The hit rate increase if we didn't consider when the cache is not empty or maybe not full, maybe something like that. First in, first out simply can determine the importance of blocks. Even though page 0 has been accessed a number of times, first in, first out still kicks it out. First in, first out simply can determine the importance of the block, or in this case maybe the page, I guess. The importance of the page, even though page 0 had been accessed a number of times, first in, first out still kicks it out from the cache simply because it was the first one brought into memory, right? This is the threat of from the first in, first out policy. Okay, I guess let me read this aside first. Lattice anomaly. Okay, yeah, if I remember correctly, Belati is the one who, what is it called? Maybe who figure out, is that the word? If Belati is the first one, the ability showed that a simple but unfortunately difficult to implement approach that replace. Okay. The best that will be accessed for those in the future is the optimal policy here. So the one who showed the optimal policy, it is hard to implement, right? Because the future is unknown. Most of the time, okay. Validity of the optimal policy, and colleagues found an interesting reference stream that behaved a little unexpectedly. The memory reference stream, okay, this one, 1, 2, 3, 4, 1, 2, 5, okay. The replacement policy they were studying was first in, first out. Oh, found an interesting reference stream that behaved a little unexpectedly. A little unexpectedly. The memory reference stream here, the replacement policy they were studying was first in, first out. The FIFO here. The interesting part, how the cache hit rate changes when moving from a cache size of 3 to 4 bits. How the cache hit rate changes when moving from a cache size of 3 to 4 bits. Okay. How the cache hit rate changes when moving from a cache size of 3 to 4 bits. Oh, okay. In general, you would expect the cache hit rate to increase or get better when the cache gets larger, but in this case, with first in, first out, it gets worse. Oh, interesting. Calculate the hits and miss yourself and see. This odd behavior is generally referred to as Lattice anomaly. to the chagrin of his co-authors. Some other policies, such as least recently used, I guess, don't suffer from this problem. Can you guess why? As it turns out, the least recently used has what it was. Let me read this again. Least recently used has what is known as a stack property. Okay. For algorithm with this property, a case of size n plus 1 naturally includes the content of a case of size n. Oh. Thus, when increasing the case size, the hit rate will either stay the same or improve. Okay. First in, first out, and random, among others, clearly do not obey the stack property, and thus are susceptible to anomalous behavior. Alright. Anomalous behavior. Okay, interesting, the stack property. So it is called the stack property. Okay. With the size n plus 1, it also include the size n. So everything in n and then plus 1, right? So it is either stay the same or increase, because the stack, what is it called? We put the new one at the top and then take out the new one, maybe something like that. Okay, let me continue first. Another simple policy, random. How many policy are we taking a look? First in, first out, random. Least recently used. Okay. Oh, wait. Okay, I guess what it means by the stack property here, we put the new one at the top, but we take out the oldest one. Maybe something like that. So the hit rate will either stay the same or improve. Maybe. I'm not entirely sure. We will find out, I guess, or hopefully. Let's see how it goes. Another simple policy, random. Another similar replacement policy is random, which simply picks a random page to replace under memory pressure. Random has properties similar to first in, first out. It is simple to implement, but it doesn't really try to be too intelligent in picking which block to evict or to take out. Let's look at how random does on our famous example reference tree. See the figure 22.3. At this one, tracing the random policy. Okay. Oh, this one. I mean, it is supposed to be random, right? So, Okay, at first it looks like the first in first out, because we are taking out the first in page here, right? And then suddenly we take out the second page here. Okay. Of course, how random does depends entirely upon how lucky or unlucky random gets in its choice, right? Depending on luck. Okay. In the example above, random does a little better than first in first out and a little worse than optimal. Oh. Okay. I mean, again, depending on the luck, right? In fact, we can run the random experiment thousands of times and determine how it does in general. Figure 22.4 shows how many hits random achieve over 10,000 trials, each with a different random seed. As you can see, sometimes just over 40% of the time. Oh, how many hits random achieve over 10,000 trials, each with a different random seed. As you can see, sometimes just over 40% of the time, random is as good as optimal, achieving 6 hits on the example trees. Sometimes it does much worse, achieving 2 hits or fewer. Sometimes just over 40% of the time. Okay. Random is as good as optimal, achieving 6 hits on the example trace. Sometimes it does much worse, achieving 2 hits or fewer. How random does depends on the luck of the draw, right? Depends on the luck. Random performance over 10,000 trials. Yeah, I mean it is random, you know. So there is that. Using history LRU. This is tracing the LRU policy. Okay. Unfortunately, any policy as simple as first in, first out, or random is likely to have a common problem. It might kick out an important page, one that is about to be referenced again. First in, first out kick out the page that was first brought in. If this happens to be a page with important code or data structure upon it, it gets thrown out anyhow, even though it will soon be patched back in. Right, similar to this figure 22.2, like this one. We are taking out page 0, even though we will be accessing page 0 later on, right? Okay, that is the drawbacks, I guess. Okay. To use first in, first out, random and similar policies are not likely to approach optimal. Sometimes smarter is needed. Okay, as we did with scheduling policy, to improve our case at the future, we once again lean on the past and use history as our guide. Right, previously, we also talking about the scheduling policy. I guess starting from this, maybe using the feedback for the scheduling QA, I guess, something like that. And I kind of forgot about this. Oh, this is using the ticket. Right, well, there is a little, what is it called? A little throwback at the scheduling policy. Lean on the past and use history as our guide. For example, if a program has accessed a page in the near past, it is likely to access it again in the near future. One type of history information a page replacement policy could use is frequency. Oh, okay. If a page has been accessed many times, perhaps it should not be replaced as it clearly has some value, right? The frequency being accessed, maybe something like that. A memory commonly used property of a page is its recency of access. The more recently a page has been accessed, perhaps the most likely it will be accessed again. A more commonly used property of a page is its recency of access. About the recently accessed or something like that. The more recently a page has been accessed, perhaps the more likely it will be accessed again. This family of policies is based on what people refer to as the principle of locality, which basically is just an observation about programs and their behavior. Okay, I think we touched a little bit about locality in the TLP section here, if I remember correctly. Okay, it is basically just an observation about programs and their behavior. What this principle says, quite simply, is that programs tend to access certain consequences, for example in a loop, and data structure, for example an array accessed by the loop. Right. Quite simply, programs tend to access certain consequences, like in the loop, and data structure, like array accessed by the loop. Quite frequently, we should just try to use history to figure out which pages are important and keep those pages in memory when it comes to eviction time. And thus a family of simple, historically based algorithms are born. The least frequently used LFU policy. Replace the least frequently used page when eviction must take place, when we need to replace the page. Similarly, the least recently used policy replace the least recently used page. Okay, this algorithm are easy to remember. Once you know the name, you know exactly what it does. It is an excellent property for a name. Right. Okay, but the frequency and also the recency. Whether we what is it called? Whether the page has been accessed many times, that is the frequency. Like how many times the page accessed, and then recency is the page recently accessed, right? That is the different least frequently used and least recently used. To better understand LRU, let's examine how LRU does on our example reference stream. You go 22.5 page 7 shows the result. From the figure you can see how LRU can use history to do better than stateless policies such as random or first in first out. In the example, LRU affix page 2 when it first has to replace a page because 0 and 1 have been accessed more recently. It then replaces page 0 because 1 and 3 have been accessed more recently. In both cases, LRU's decision based on history turns out to be correct and the next reference are thus hit. Thus in our example, LRU does as well as possible, matching optimal in its performance. Okay, we should also note that the opposite of this algorithm exists. Most frequently used, the MFU, and most recently used, the MRU. In most cases, not all, okay, these policies do not work well as they ignore the locality most programs exhibit instead of embracing it. Okay, let me read the footnote first here. Okay, we cooked the result. But sometimes cooking is necessary to prove a point. Okay. Figure 22.5. This one, tracing the LRU policy. This is the compulsory miss, I guess, or the cold start. The cold start miss. Then this one is hit. Wait a minute. Oh. Okay. It also move the order. Alright. So we access. Wait, this is least recently used. Right. Oh. the least recently used is the first one here. I assume. Okay. 0 hit, we move 0 to the right here as the recently used. I assume the recently used is the red one here. And the left one, the leftmost, I guess, is the least recently used. We are accessing 0, okay, we are accessing 1. 1 move to the right, okay, something like this, right? And then we are accessing 3 but miss. And previously in the case, the least recently used is 2 because we haven't used 2 since this one, right? So we move out that from the case. And then we add 3 on the case as the recently used 1, trying to hit 0, trying to access page 0, and then hit, move the page 0 at the right, the recently used page, trying to access 3 again, hit again, move 3, move page 3 as the recently used page, trying to hit 1, move page 1 as the recently used page, and then trying to hit page 2. It is a miss because there is no page 2 in the case, so we need to evict the least recently used, and that is page 0 here, because we haven't used page 0 since this one, right? So we move out the page 0 and then insert the page 2 here as the recently used page, and then we try access page 1, and of course we hit because page 1 is in the case, and move the page 1 as the recently used page, something like this. Okay, and then let's take a look at the aside. Types of locality. There are 2 types of locality that programs tend to exhibit. The first is known as spatial locality, which states that if a page P is accessed, it is likely the page around it, say page P negative 1 and or page P plus 1, will also likely be accessed. We can think of spatial locality as the surrounding, maybe surrounding locality. So if the page P access the surrounding, and that is page negative 1 or page plus 1, will most likely getting access to. And then the second is temporal locality, which states that pages that have been accessed in the near past are likely to be accessed again in the near future. Okay, near past. Alright. Are likely to be accessed again in the near future. The assumption of the presence of this type of locality plays a large role in the caching hierarchies of hardware systems, which deploy many levels of instruction data and the text translation caching to help program run fast when such locality exists. The assumption of the presence of this type of locality plays a large role in the caching hierarchies of hardware systems, which deploy many levels of instruction data and address translation caching to help program run fast when such locality exists. Of course, the principle of locality, as it is often called, is no hard and fast rule that all programs must obey. No hard and fast rule. Okay, indeed, some program access memory or disk in rather random fashion, right? And don't exhibit much or any locality in their access stream. Thus, while locality is a good thing to keep in mind while designing cache of any kind, hardware or software, it does not guarantee success. Right? This is just another method, I guess, but we might not be utilize the cache efficiently, I guess, when we implement the spatial or temporal locality here. It's just something to keep in mind. Rather, it is a heuristic that often proves useful in the design of computer system. Alright. This workload example here. Yeah, I think we also talking a little bit about locality in the TLP. In case anyone wants to take a look. A workload example. I guess. Oh, hello, that funny. Hey man, are you using i3? Yes, this is the i3 window manager. i3. In case anyone curious, this is the i3 window manager. I put that in the chat. Okay, I guess let's continue this section on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.